In the previous section, we covered how to tune our models and how to select the best model for the job. In this section, we're going to take a step back towards the value proposition of machine learning and discuss how to implement a model after it's been tuned. Then we're going to cover how to persist it to disk. In the end, this is a step that differentiates practical machine learning from research. We'll start this section with a brief discussion over the next steps in the machine learning lifecycle. Next, we'll get technical again, covering model persistence and some considerations you'll need to make when migrating a model into a production environment. Finally, we'll put together a simple Flask app that will serve up model predictions remotely. In this first video, we're going to back up from our focus on technical components to discuss how to operationalize our model in an actionable way. In this video, we'll first discuss what outputs we'll need in order to make a model actionable. Then we'll cover the post-processing stages required to get us to that point. Finally, we'll cover the actual persistence in Scikit-Learn. What you're going to find is that simply generating model predictions doesn't satisfy a business requirement, generally speaking. Most of the time, your model outputs will need to be filtered, transformed, or fed into another process in order to make them actionable in some way. For the sake of discussion, let's consider the heart disease model. We have 5 outputs, each indicating some type of severity. Perhaps the surgeon who enlisted our efforts is only interested in category 3 and whether it's predicted with a probability of 0.3 or greater. In this case, our model output will now become binary. Is it category 3 and 0.3 or higher or not? 0 being no, 1 being yes. Let's dive into an example over in our heart disease notebook. So at this point, we've already built our model selection pipeline. You can see above we just left off with our partial dependency plots. Suppose again that our board of surgeons really only cares if the prediction is of class 3 with a probability greater than or equal to 0.3. Let's write up a small function here that we can test out on some of our probabilities that we'll predict here. This function is going to take 3 arguments: the predictions, which is actually a matrix. We're going to use predict proba, the class that we're interested in, which we've mentioned is 3, and the probability, which we'll use as 0.3. In the first step here, we'll get the row argmaxes, which show us the actual class that was predicted by the classifier. In the next step, we'll grab the probabilities for the class of interest, which is class 3. Finally, we will use a unary operator to come up with the bitwise AND function of whether the argmaxes, meaning the row max predicted class, is equal to the class 3 and the probability is greater than or equal to 0.3. And we'll return it as a type int rather than a Boolean mask. If we run this, keep in mind, by the way, we're using the probabilities. It's a matrix 2D. If we run this, you can see we get a vector of 1s and 0s. I'm going to add something in here real quick, actually. We can validate this again using a Boolean mask. If we take these outputs, cast them as a Boolean, and grab the third class, you can see that all of these are the majority prediction with a probability greater than or equal to 0.3. At this point, we can talk about model persistence. After you've fit a model and you've predicted, we need to put it on a disk. So remotely or locally, we can load the model up and generate new predictions with new data. Scikit-Learn makes model persistence extremely easy by bundling in the joblib external inside of the scikit-learn.external's joblib submodule. This is a wrapper for the pickle module, which you might be familiar with, which is actually going to optimize the compression we can use on NumPy arrays when we store them. Since Scikit-Learn uses so much NumPy internally, this is the most efficient way to store our models using joblib. Note that there are several cases where pickling something is not going to work for us. If one of your custom transformers includes any kind of unbound method, if any class contains a logger, for instance, in some other corner cases, we might get a pickling error. Nothing we've written here is going to show us that error, but if you encounter any of that, chances are you have an unbound method. For anyone who's familiar with like Java or anything and typically uses interfaces, this is why in Python, and specifically with Scikit-Learn, we use strings as keys for different mapping functions. So for instance, when we use logistic regression, we actually pass a string LBFGS for the the optimizer rather than the function, because that way we're not trying to pickle an unbound method later. So that explains that, in case you were wondering. We can go ahead and write it to disk. We're just going to use the joblib.dump function. We're going to grab out the best estimator from the grid search. We could theoretically pickle the whole search, but if you fit 50 different models, you may not want to store all the different CV results for all those. So we're just going to grab out the best estimator, store that, and we're going to use this right here, pickle highest protocol. This is something that's going to come up in our next video, but this is basically the protocol for the major version of the language, so Python 3. Okay, we can go ahead and store that, and then we can prove here that the model location will exist on disk, and that we can load it up and run it through that same post-processing function to get the same results, which you see is exactly the case. We can even use one of Jupyter's magic functions here to show that it exists on disk, right there.